Usually when somebody claims that Einstein was wrong, they're a bit crazy. And so the ultimate goal of this talk is to convince you that I'm not crazy. Or not about this, but and rather to provide you with some evidence that Einstein's theory of diffusion may break down when you consider the extreme behavior of many particle diffusions. So that is the behavior of the particles that go the furthest or the fastest out of a great many of particles diffusing in a common environment. So in place of Einstein's theory, I'll offer the glimmer of a new theory of extreme diffusion and a new extreme diffusion coefficient to complement the classical Einstein diffusion coefficient. I'll also describe the mathematical underpinnings of this work, in particular in relation to the realm of integrable probability and stochastic partial differential equations. So the first half of this talk, I'll kind of put on a physics hat. I'm not a physicist. And the second half will be more math-focused. But let me start by explaining to you why extremes might matter in many particle diffusions. So this figure shows the rapid and manifold mutations of COVID-19. So most mutations had minor effects, but some variants, generally those that had the largest jump in terms of the number of mutations measured in the vertical direction over time, became more contagious and virulent. And so we saw time and time again, it was these extremes in the diffusion in this genetic space that defined the trajectory of the pandemic. There are many other examples where extremes, the particles that diffuse the fastest or the furthest, control the behavior of a system. In the transmission of signals in your cells, and you have neurotransmitters, and you don't need all of them. You just need a very small fraction of them to cross barriers. Also, in astrophysical contexts, the photons that we can observe from things like supernova shock are the ones that go the furthest and arrive to us first. On the internet, the ideas that spread are those that go the furthest, and they're usually not the good ideas, but nevertheless, they do spread. And likewise in pandemics, early on at least, in a pandemic, it wasn't nearest neighbor spreading. It was people who got on buses or airplanes and went far who spread and determined the rate of at which it spread. That was Italy in the first few days. So none of these are simple or idealized diffusions, yet still a fundamental understanding of the behavior of extreme particles in many particle diffusions should play an important role in modeling the nature of these various types of systems, and also in interrogating the hidden environment in which such a diffusion occurs. The scale of many particle diffusions vary wildly, from ecological all the way to astrophysical scales. And because there are so many particles, if you have a theory that accounts for 99.9999999% of particles, but you have 10 to the 12 particles, that leaves an immense number unaccounted for. And they may behave very differently. And so we seek to understand these atypical particles and learn from them. So at this point, I hope I've convinced you that extreme behavior in many particle systems may be important. And now I want to convince you that Einstein's theory may fail at modeling extreme diffusion. And in its place, I'll offer a glimmer of a new theory. But first, let's recall the origins of Einstein's theory of diffusion. So Robert Brown, famed botanist, and actually there's a mountain in Australia named after him, observed the erratic motion of pollen in water and recorded its statistical behavior. So he also, very intelligently, he looked at what happened when the pollen was toasted. Why toast it? Well, because pollen is alive. If you toast it, it's dead. And he also compared that to shavings of rock and coal. And what he found is that the same erratic motion would occur either way. And so this convinced him that the motion that he was seeing was extrinsic. It was an effect of the environment acting on the pollen and not the other way around. It took about 100 years for Einstein and others to understand that there was a hidden environment of chaotic water molecules. You see how I timed that? I didn't even touch it. Okay, which was driving this erratic motion through all of these collisions. So this led them to postulate this very simple random walk model in which they were able to produce concrete predictions about the variance and the distribution of particle displacement as a function of time. And it was soon after that Perrin, who won a Nobel Prize for this, confirmed the theory experimentally. But even early on, it was recognized that there were shortcomings to Einstein's theory. For instance, in short enough times, the motion that you would see would be ballistic because of these collisions. Okay? So of course, we're going to try to show another shortcoming of the theory. Now, the Einstein model was really developed to only study the motion of a single or a small number of particles. Yet it's widely applied to model systems with many, many particles diffusing together. So it's too much to hope that you could numerically or mathematically capture the behavior of the tracer particles and all of these sea of particles that are bombarding it. And so the Einstein model completely throws out all information about the environment except for one thing, which is the Einstein diffusion coefficient. And it treats every particle as independent within that. So here's a continuum version of this. The Einstein model, if you imagine you have n particles, you're diffusing according to independent Brownian motions. And let's say you start all at that star. The three trajectories that you see will be completely independent of each other. Now, of course, this model misses something. It misses the fact that the particles are in an environment together. And when they're near each other, they may feel similar forces from that environment. So the random walk in random environment model, or class of models, treats the environment instead statistically as some sort of random field which has short-range correlations in space and time that bias the motion. So here's a stochastic differential, or a system of stochastic differential equations. I'm not going to focus on this one, in fact. I'm just writing it so you can see. So you can imagine you have this field, and at different times, the forces of the field, there are little arrows and different intensities that are pushing you in kind of common ways. And so what this does is it couples together the behavior of all of these particles in a common environment. So in short enough times, you might expect that if you start a few particles near each other, their trajectories will stay near each other until some time when they'll separate, like leaves in a stream that kind of hug each other until they go their separate ways. So for the rest of this talk, I'm not going to focus on these continuum models. I'll focus on a very simple discrete models of random walk in random environment, mainly in one dimension, but we'll also talk a little bit about 2 and 3 dimensions where things get even more complicated and something that we're working on. So this is the one-dimensional random walk in random environment model that Guillaume Barraquin and I began studying a few years ago. There's no politics in this, despite, well, okay, maybe there's a little bit. So you have particles, these are these little black dots, and they're moving in a discrete space and time parcels. Time is measured in the vertical, space in the horizontal. And the rule is that every site in space and time is colored randomly on the spectrum of left to right, blue to red. And if particles are in the same location, they feel a sort of a weighted coin. So if it's very blue, you might have a high probability of moving left. Most of the particles might move left. And they do that according to independent coin flips. So you're using the same weighted coin at the same space-time site. That's the model. Okay? And the question asks, what happens as a function of the number of particles, the time, and the distribution of the biases? In particular, what happens to the outliers, the particles that move the fastest from this cluster of starting particles? That's the question. Okay? We need to set the model a little bit more clearly. I haven't told you what the distribution on the colors is. And in fact, in the end, we'll talk about non-nearest neighbor models with arbitrary distributions. For the moment, let's pick one very simple family. This is the beta distribution. So beta distribution is on the interval 0, 1, gives you a random number. The simplest case of the beta distribution is the uniform distribution on the interval 0, 1. 0 you think of as left-leaning, 1 as right-leaning. On the other transition, if we take this symmetric case of alpha and beta equal, you get to what I would call a purely partisan model. Every site is either perfectly blue or perfectly red, and in which case all particles just follow the path directed by that. So that's basically the Einstein model with one particle. They all get clustered. On the other extreme, as alpha and beta go to infinity, you get a system which is entirely white, in the sense that every coin is 50-50, and every particle articulates an independent, simple symmetric random walk. And so we're interested in understanding, as you modulate this, in particular, you compare alpha and beta 1 and alpha and beta 20, or no, infinity, what will happen to the behavior of extremes. Yes? Yes. So it's changing. In fact, it's independent in space and time. There are models where you fix a random environment that is constant in time, and there are different behaviors that occur there. So this is not that. This is, of course, the setting we should have in mind is some fluid that's kind of quickly mixing, and it's bombarding particles in different ways in space and time. So here's an instance of running both models. I'll call the Einstein model and our model for about 1,000 particles. I didn't actually count. And the physical question here is, what if I didn't tell you which model was which? What if you didn't see the background? Could you tell the difference between the two based on the way that the particles behave? That's the question. Now, you might hope to see this at the level of the bulk, right? You know, you look at the typical particle or the density of particles, and you might want to see it. So here's a typical particle in both, a randomly chosen out of the 1,000 particle. And here's the gradient of occupation densities. And you see, and there are theorems I'll cite in, later on, they're basically the same. Both of them kind of look like Brownian motions. And the densities, well, if you squint, you can't tell the difference. If you look closely, you see that in our model there might be some favored paths, you know, areas where particles get rooted a little bit more likely. But that's a very small scale thing, and in a real physical system, you probably wouldn't be able to distinguish. So the bulk is not the place to see this. What about at the extremes? Of course, you can't see the extremes here. So let's look a little closer at them. So let's go back to this picture. And let's ask the question of what's the time at which there are no particles on the left boundary, right? At each time, you kind of can split your particles left and right. And is there a difference there? So indeed, there is. So in the Einstein model, at each epoch, you're basically splitting the population in half in some binomial way. And so you expect log base 2 of n time until you get nothing left on the outer boundary. And in fact, the reality is the number will be random, but it will be of order 1 around that, independent of n. On the other hand, in our model, at each time you take a random uniform 0.1% of the particles and move them left. And it's a nice application of the law of large numbers. You need to take a log, but to show that the time it takes is log base e, or natural log of n. And so it's much shorter, actually. And moreover, the fluctuations of that exit time are of variance, actually also proportional to log of n. So it's much more wild, the time at which it separates, and because you have all of this randomness. But again, this is not really a physically relevant observation, because in a real diffusion, there's no notion of the boundary of the diffusion. You don't have this discreteness, so that's not the right thing to look at. So what I'll argue is more valuable is to look at the outlier location. So you look at just the location of, say, the left or the rightmost particle as a function of time, and you ask, how random is it? And when I say how random it is, what I mean is there are 2 levels of randomness. You choose an environment, and then you choose n random walkers in it, and you observe the location. Then you repeat that 1,000 times. And you build up a histogram, and you ask, how wide is that? How random is that location? And of course, in the Einstein model, there's only one level of randomness, the sampling. In our models, there's the environment and the sampling, so it should be more random. And the question is, how do these 2 effects play out over time, and can we use them to somehow uncover the environmental contribution to the randomness of the outliers? So here is a sort of overview of results. What we've shown is that extreme particles actually carry a lot of information about the hidden environment in which they're diffusing, in particular through a new power law and a new extreme diffusion coefficient. So what I'm showing here is the result of theoretical work coming from the n, the number of particles, to infinity limit. These are these dashed lines. And also numerical simulations that confirm the theory holds down to realistic, so 10 to the 7, for instance here, values of n, the number of particles. I'm going to focus on the mathematical underpinnings of this for the later part of the talk. But let me first kind of explain what's going on in this. So the plot shows in the horizontal direction time, and it's natural to scale time by log n. This is the time at which things start to get random anyway in terms of the outliers, otherwise you hug the boundary. We look then in the vertical direction at the variance of these outliers, these maximal particles. And we're plotting everything in log-log coordinates, so power laws are linear, slope is the power, and the offset is the coefficient. Now in the Einstein model, labeled by the word Einstein, it's a very simple application of extreme value theory, I'll go into that later, that shows that the variance of the outlier ends up basically having a linear power law and with a coefficient that depends just on the Einstein diffusion coefficient. Okay, so not much there. On the other hand, in our model, labeled Barraquan-Corwin, you see, this is this red curve, you see that there's a big increase in the variance early on, and we already saw that this was going to be the case because the time at which you separate is pretty random. And then it resolves into a more moderate growth, and then at some later time it actually kind of seems to coalesce back with the Einstein curve. So at first you might hope, well, you can observe this intermediate region. But unfortunately, this intermediate region happens between times of scale log n and log n squared. And for a realistic system, that's maybe a decade or so. And so you wouldn't, it's unlikely, I'm not sure, but it's unlikely that you'll actually see that experimentally. And so, is all lost because the two kind of coalesce. Now, what we've shown is that not all is lost. So in the following sense, so remember, the Einstein variance was just from sampling, and ours had a contribution from the environment and from sampling. If you subtract the Einstein curve from our curve, you recover this other power law. And this other power law lasts for all time. And it has a different power. It has a slope 1/2, and it has a different offset. And that offset contains information about the environment. It actually contains the variance of the randomness of the environment. I'll explain precisely in the later part of the talk what this means. And so that coefficient, this extreme diffusion coefficient that you can in principle read off from making a real observation about this behavior of the maximum and subtracting off this behavior of the Einstein curve, it actually tells you something that you missed by just looking at typical particles. So this is the kind of set of conclusions, and I'll substantiate all of this mathematically. But before I do that, let me kind of indicate some perspective on experiments. This is numerics and theory, and of course we'd like to be able to observe these things in real experiments and test whether the model of Einstein or our model is a more accurate model for the world. And so this is experiments being developed in my brother's lab in University of Oregon. During COVID, my mom said we should talk more. So this is the way we know how to talk. Okay, so what we're doing is we're currently, actually some of this started at KITP. Okay, so we're currently developing what I think will be the first experiments to precisely measure the extreme statistics of many particle diffusions. And so one type of experiment, which is caricatured here, involves colloids or fluorescent dyes diffusing in fluid in quasi-one-dimensional capillaries, in which you can vary the type of fluid, the number of particles, the type of particles, the length of the capillary, and the temperature, for instance. And you start them all concentrated on one end, and then you measure first passage times, and you ask how that varies as you repeat the experiment. Now, this is what the actual apparatus looks like. We've built it, though it's hard to find people to run experiments. And these are very small capillaries. You centrifuge it, that sends the particles all out, and then over the course of a few days, you see the particles diffuse past this camera. So there are some challenges in actually understanding how to reconcile, first of all, gathering enough data, how to reconcile this experiment against the theory, and also trying to understand influences like temperature and long-range correlations in the environment, interactions between particles and interactions with the environment. All of these questions are ones that we're kind of in the process of thinking about as we try to run these experiments. Now, there's another experiment, which I'll admit I don't think actually will be captured by our theory, but we're still running it, which has to do with photons moving through highly scattering media. The nice thing here is that you can interrogate 1, 2, and 3-dimensional systems. You have these tubes or disks or spheres, and you send a femtosecond laser pulse in, and you measure the passage time of particles moving through scatterers. And you try to understand the statistics of that. And here, there may be other effects. Maybe not, but one could imagine quantum versions of models like this. Maybe one doesn't deal with photons, but other types of particles. There could be some very interesting additional physics that goes into this sort of setting that we're interested in understanding. Now, the ultimate goal, lost something. Okay, we're back. The ultimate goal of this work is to try to understand how internal fluctuations of an environment manifest themselves in the motion of many particle diffusion. And so a key differential measurement in the experiments will be to that really should be able to disprove the applicability of Einstein's theory is to contrast particle media pairs that have the same bulk behavior, in other words, the same Einstein diffusion coefficient, but very different internal dynamics. For instance, in the colloid experiment, you could consider a Newtonian fluid, water and glycerin, and compare that to a polymer melt and tune the two of them to have the same diffusion coefficient. And then what you would do is you would ask, how do the extreme behaviors? If Einstein is right, the extreme behavior should be identical. If Einstein is wrong, you'll see a difference. In the other setting, you could consider a single scale versus all scale scatter critical opalescence, for instance. The hope is that once you've disproved Einstein, we'll be able to show that the extreme behavior actually follows our theory, and we'll be able to build up tables of extreme diffusion coefficients, which will carry new information about the internal dynamics of the hidden environment. So in this way, extreme diffusion may also provide a microscope through which to interrogate and differentiate between different types of systems where it's hard to observe the internal dynamics of the environment. And ultimately, I think this is the goal. This is the sort of pipe dream. Okay, so based on the first part of this talk, you may think that I set out to disprove Einstein or develop this theory or anything like that, and that's far from the truth. So actually, this came from interest in mathematics in the field of integrable probability. So this is the core area that I work in. Of course, things like this Simons funding allow you to do things that are not in your core area, and this is why it's been very exciting to do these types of things. So integral probability has to do with the role that certain algebraic structures, things like symmetric functions, quantum groups, solutions to the Yang-Baxter equation, how these can give rise to probabilistic systems and tools for their asymptotic analysis, which ultimately reveal universal behaviors that go beyond those specific models. So the model I was talking about, this beta distributed random walk and random environment model, it first came out of that context. And the fact that it had all of this fascinating behavior first came out from understanding how to solve the model using these tools. So in the rest of the talk, I'm going to describe first the precise version of the results from the first part of the talk, so you really can see what that looks like, not just graphs. And then I'm going to describe one technique from integral probability to give you a flavor. And if I have time, I'll kind of zoom out a little bit and maybe prepare you for Norman's talk in some sense. OK, so let's back up and consider the mathematics behind classical Einstein model, the classical Einstein model. So this is like graduate probability 101. Here, the Einstein model, of course, you could have a drift on the probability. This is, let me just imagine alpha and beta are equal so that you have an equal probability of every particle moving left and right. It's a fair coin model. We record the location at time t of a single particle. We'll call that x sub t. That's like the red particle there. There are three classical results in probability theory you've probably heard. The first, the law of large numbers. What it shows is that if you look at a single particle, and you look at its velocity, so xt over t, then it will converge to the mean of a single jump. You have a sum of IID of independent, identically distributed random variables. You get that mean. The central limit theorem tells you that if you center by that and you scale by square root of t, the distribution, that's where the randomness lives, the distribution converges to this normal Gaussian 0, 1 random variable. And this is describing, in other words, if you look at the density of particles at the top, it's kind of going to approximate a bell curve in the right scale. Now, the large deviation principle quantifies the likelihood of seeing a random walker do something in excess of what it's supposed to do by the law of large numbers. And you might say, who cares, right? These things are unlikely. Well, so first of all, how unlikely? By the law of large numbers and central limit theorem, we know that there needs to be a very rapid drop-off in the probability, and it turns out, in fact, that the probability of having this excess time behaves like e to the minus t times something called the rate function, or written in terms of the log of the tail probability is what's here. Now, this rate function encapsulates kind of the decay of the probability, and Kremer teaches us that it's given by the Legendre transform of the cumulant generating function for a single increment. So there's a general theory that just tells you how to compute this unlikely probability event. In the case of the simple symmetric random walk, it's this entropy function, this very simple function on the bottom here. So you might think that large deviations don't matter because they're so unlikely. But of course, if you look at this formula for the behavior of the maximum of n particles, you see that if you want to know kind of where to center yourself when you look at the maximum of n particles, you should roughly look around where the tail probability is like 1 over n. Right? Because if the tail probability, the probability xt is bigger than little x, it behaves like 1 over n, then you have 1 minus 1 over n to the n, which is like e to the minus 1, right? So it's something transitioning from 0 to 1. That's where the fluctuations will live. And so you see now that if n is very large, you need to look deep in the tail. So in particular, if you have, say, n particles and you look at a time t, which is of order log n, then just through a simple calculation, you see that the large deviations determine where that centering will be, okay? And it will actually be, you'll get it, you'll find that, critical x by solving for I of x equals, I wrote it down, log n over t. Okay, so there's some simple kind of inverse problem to the large deviation rate function that you need to solve. Now, if you look at a later time, so as you go deeper and deeper in time, you go longer and longer, then it's no longer large deviations that controls the behavior of the maximum, the location of the maximum. There'll be a transition towards the moderate deviations. And eventually, if you kind of think of n as very small compared to time, the central limit theorem will again control the behavior of the maximum. If you have one particle, central limit theorem definitely kicks in. But so from this logic and from understanding these moderate deviations, this transition, you can completely recover the Einstein curve that I talked about earlier on and the whole kind of theory around that. So let me not do that, though, and let me move back to the RWRE model. Okay. So let's try to be a little bit more precise. Here, the environment is a collection of these independent, identically distributed biases, which I'll call BTX, with some common distribution on 0, 1. The BTX gives you the probability that if a particle is at position x at time t, it will jump to the, I guess, to the right in the way I've drawn it. And 1 minus BTX is the probability that goes to the left. Every particle jumps with independent probabilities given the BTXs. Okay? So there are two levels of randomness here. This black-faced bold P is the probability measure on B. It's a product measure withdrawn from some distribution. For instance, you choose each one uniformly on 0, 1, and you get this sort of picture of the random checkerboard of colors. Now, given an instance of the environment, we'll call this sans serif B, P sub B, the probability measure on independent random walks in that environment. Okay, so these are the two levels of randomness. Now, what happens to the law of large numbers and CLT? Well, by self-averaging, and this is a result of the group down here, almost surely with respect to the way you chose your environment, a typical particle, so if you just sample a single random walker in that random environment and you look at its trajectory, it will satisfy the same law of large numbers and the same central limit theorem, in fact, the same sort of functional Brownian motion central limit theorem as in the averaged environment. So in other words, if you replace this random environment, the uniform 0, 1, by the pure white environment, and you look at a typical particle, and then you compare that to the typical particle in the random environment, almost surely they will look the same. And this is good. This is good news, because it would be a bad model if it didn't recover what Perrin observed, okay, or others. Now, there is also a general large deviation principle. But the thing is that the mapping from the law on the environment, this distribution on the interval 0, 1 that gives the coloring, to the rate function is completely inexplicit. So that's a bit of a problem. Moreover, if you look at the object here, so this is the tail probability. This is a random variable. Okay, it depends on the instance of the environment. And you're asking kind of the tail of this heat kernel, this random heat kernel. You take the log, you divide by t. This is such a coarse scaling that what you get is deterministic in the limit. But we want to know how the environment's randomness affects the behavior. So we should look for the correction to this, the sort of central limit theorem type result on this large deviation that will then filter into the behavior of the outliers. So this is what I'll explain in the very, again, in the context of this beta distribution. So I'm going to give the results again for alpha and beta equals 1. Here's the result. So if you look at the rate function for this uniform environment, which we've been talking about, and it actually is simpler than in the simple symmetric random walk. the presence of this uniform random variables, the large deviations is just 1 minus square root of 1 minus x squared. This is a simpler function than the entropy. It's certainly simpler to invert than the entropy function. Now, moreover, if you look at the tail probability, the probability that you go further, by a factor of x than you expect, so the average here should be that, the law of large numbers occurs around 0, and you want to go past that. That plus the rate function times t actually fluctuates in a scale of t to the 1/3, so not a central limit theorem scale. And the limit that you get, the statistical limit, is something called the GUE Tracy-Whittem distribution. This is something first coming from random matrix theory, and then it's very prominent in the world of the Kadar-Parisi-Zhang universality class. Okay? It, of course, came as a shock to us that this was the case, but now we understand this much better. So there are variants of this result for all values of alpha and beta. I won't give them. But the thing that is delicate here is that it is conjectured to be true for any distribution. But we don't know how to prove that. That is a universality result we do not know how to prove about the large deviations. On the other hand, if I move into, so this result, which has to do with large deviations, as I said, this has to do with the behavior when time is of order log n. Okay, I kind of hinted at that before. So this result really captures the behavior in this moderate time. The behavior I'm actually most interested in is long time. And so we'll come to that, and there'll be a stronger result I can give. Let me just define one thing quickly, though. We saw that the very important thing to understand is what's the probability under my random probability distribution given the environment, what's the probability that your tail is about 1 over n? What is the location at which the tail probability is about 1 over n? Because that's the thing, that's the place where the maximum should roughly fluctuate around. So we're going to just define that. We're going to call that the environmental, this mth nt. This is like the location at which the environment kind of pushes you to look. So when I talk about the variance due to the environment, I actually mean the variance of this quantity, this centering by this location of what I'll call the nth quantile of our distribution. Okay, so the next result probes what happens when you go to longer times. And so what's given up in this upper right picture, I'm actually now considering 3 choices of environments. Okay, so one is the inlay shows the density, or in fact there's a delta, so not quite the density. But one is the uniform, that's this thing I wrote as beta. Another is this quadratic looking density. And the third is actually, and it's hard to see, but it's a sum of 3 delta masses, one at 0, a half, and 1. And it's symmetric. So the tuning of these environments is such that the mean is a half, and the variance is the same of that of a uniform, which is a quarter, or sorry, which is a 12th. So all 3 of these have the same mean and variance, the environment themselves. Now you look at the variance due to the environment, the variance of the location of this quantile, this nth quantile, the location where you should center around. And you see, well, in 2 of the models where the densities are similar, they actually kind of look similar. But the third, this delta, looks very, very different in this medium time regime between time of log and log n squared. But once you move into this long time regime, the effect is basically negligible. It's only the knowledge of these first 2 moments that actually matter about the environment. And so this is actually indicative of this theorem. I won't go through the details of it, but what it says is that if you look in the moderate deviation regime, you look at a time scale which is not linear in this L parameter, but like L to the 3/4, so there's some transitional regime, that the tail probability is universal. It only depends on the first and the second moment of the environment. And actually, there's a stronger result, which is that you can identify the universal limit of the tail probability as the solution to a stochastic differential equation, something called the multiplicative noise stochastic heat equation, the logarithm of which is this KPC equation. And the only remnant of the environment is in the coefficient in front of this multiplicative noise term. This sigma squared is the variance of the environment. So from this result, you can then prove, well, that's where you recover this variance through the environment curve, this blue curve, okay? And that's where you actually get this power law, and that's where you get the relation between the environment and the coefficient of the power laws by kind of using this relation. Now, what I want to describe to you is, so here I've kind of given you a universality result about nearest neighbor random walk in random environment. But of course, why restrict ourselves to nearest neighbor? It's very natural to consider a much more general class of models. So the model you should have in mind here is kind of depicted in the picture. Maybe I'll start with the picture. You have space and time, space again horizontal, time vertical, and out of every site you have these red arrows, and the red arrows are random. They're drawn from some distribution on how you can kind of allocate mass 1 to a bunch of different points. So, there's some probability of going left, right. One concrete example is to consider a Dirichlet distribution on the numbers -2 through 2. What that does is it produces some kind of random point in a simplex of points that are non-negative and sum to 1, which you can think of as giving you the probability that you move 2 to the left, 1 to the left, 0, 1, or 2. And so you kind of, you create this random environment, which is all these red dots. Now here's the sort of more general setting, a probability measure on probability measures. Don't worry about that. And now the question is, given an instance of this random environment, what happens if you run many particles in that environment? So you start, say, 1,000 particles at the bottom, and now you let the particles follow these arrows with probability given by the width of the arrow. Now let me just note one other thing in this picture. What are these black arrows? The black arrows represent what is the sort of mean of the distribution at each point. Okay, so if I have a lot of red going in this way, then the mean will kind of shift in that direction. If a lot of red goes this way, the mean shifts. This is like the microscopic environment, how wildly mixing the drifts are inside of that environment. So what have we shown? So we've shown that if you look at the maximum, what I'll call max NT, the maximum of those n particles, the location, the variance of that maximum, or in fact, the maximum is the sum of 2 independent contributions, but the variance of the maximum is approximately the variance of this environmental term, this thing which measures, given the environment, where is the heat kernel, where is the tail probability, roughly 1 over n. The variance of that quantity plus the variance due to sampling and random walks in the Einstein model, which has the same diffusion coefficient, the same Einstein diffusion coefficient as this. So in other words, if you replace all the reds by their average values, so in the Dirichlet you replace everything by a fifth, 1/5, 1/5, 1/5, some symmetric, simple case. And so this variance due to sampling is easy to compute. This is the consequence of the calculation I hinted at before. It grows linear in t with a coefficient that's proportional to the Einstein diffusion coefficient of the averaged environment. But what happens to the variance due to the environment? So this grows, as I teased before, with a power law t to the 1/2, and a new coefficient, this lambda x. And what is that coefficient in the context of this more general model? Well, it's proportional, so you have a numerator, denominator. The numerator is the variance of the black arrows. It is the variance of the drifts created by the environment over space and time. The numerator is just the difference between the Einstein and this extreme diffusion coefficient. So by studying the maximum and removing the sampling term, you can, in principle, recover this power law and recover this observation of the environment. So it is a new statistic of the environment that should be observable in the tails. Or to kind of paraphrase Dostoevsky, if you want to learn about, he says, if you want to learn about a society, look in its jails. So if you want to learn about an environment, look at the extreme particles, is my way to say that. Okay, the way that this result is, of course, one goes through and recovers this by proving also a convergence result to the KPZ equation. And I won't go through that. There's very interesting mathematics there, but I won't have time for that. So what I want to do and of course, here's verification, various numerical verifications of all of these results. Okay, I want to spend the remainder of this lecture explaining one idea in how do you analyze this, this large deviation for the beta random walk-in random environment. And we'll give you a flavor of some ideas in integrable probability. So first, before we do that, let's just go back to the simplest setting of the simple symmetric random walk, okay, or the symmetric random walk. The tail probability of a symmetric random walk, well, of course, you can write it in terms of binomial coefficients, but you can also solve a recursion relation. Right? Your probability is related to your probability of your predecessors. Now, this recursion relation is ripe for solving by Fourier theory, by Fourier series, or by writing it as sums of binomial coefficients. Now, either way that you do that, you need to eventually take asymptotics. And let me just give you a sort of reminder. If you want to take the asymptotics of a binomial coefficient, you could, of course, use factorials and use Stirling, or you can actually just write immediately a complex contour integral for the binomial coefficient using the residue theorem. Now, this is nice because you can then, let's say you want to look at the probability that you're at the origin. You can express this in this sort of Laplace asymptotic form, where when you take n to infinity, all you care about are the behavior around critical points of this functional. So this is simple, fairly simple, but it is kind of foreshadowing part of the analysis that happens in the context of the random environment. Okay, so let me now move to the random environment and tell you what happens. So in the context of a random environment, you still have that the tail probability solves a recursion relation. And it's actually a very simple one. It's something called a random average process. What you do is you say that ZTN is the random average with, say, uniform B of the value at t minus 1 n and t minus 1 n minus 1. So you're just kind of randomly averaging your predecessors. And these random averages are random in space and time. If you repeat this recursion, you find that it relates to the tail probability that I'm interested in. So how do you diagonalize? How do you solve this random recursion relation? You can't use Fourier theory directly because it's not constant coefficient. It's not homogeneous. You know, there are problems. So what you do instead is you look at the moments of that recursion relation. Okay? So you choose some collection of locations n1 through nk, and at time t, you take the product. You call the expected value over the random environment, right? Because remember, these things depended on the b's. You average out over the b's, and you call that UTN. Now, if you look at UT plus 1n, of course, you can replace each of these z's by the predecessor, by the term from the recursion. And then you can expand. And you just use the binomial theorem. You get at a binomial coefficient, and you need to compute the expected value of a mixed moment of b and 1 minus b. And when you do that, in the case of the beta distribution, you get a very simple coefficient. You could do this for any distribution, and you get complicated coefficients. This turns out to be a nice coefficient for reasons I'll explain. So you get a recursion relation for the moments in terms of previous time moments. And it's actually a triangular relation. So if you have, if you could solve this, you would be in good position, because you would know all of the moments, and you could recover the distribution from this. So it actually suffices to kind of consider the moments in this Weil chamber where the n's are ordered. And if you had, for instance, so this is what happens when all the n's are the same. If you had clusters of n's, you know, n1 equals n2, and then n3 equals n4 equals n5, then actually what will happen is you'll get a direct sum of these types of recursion relations in each cluster. So the question becomes, how do you solve this complicated recursion relation? And the good news is that if each of the ni's is different, then actually there's no interaction, and the behavior of the system is kind of just the n-fold direct sum of the one-dimensional recursion relation in the symmetric random walk, which could be solved by simple Fourier theory. So the whole idea, which goes back to Hans Bethe in the 30s, is to try to rewrite this system as a sort of n-free body system with two-body boundary conditions at the end boundary of the Weil chamber. And let me explain how that works. In particular, I'm going to give you a result, and then I'll tell you how it relates to something called or an example of a non-commutative binomial theorem. Okay, so the result here says, consider a function of, say, k variables, n1 through nk, without restricting to the Weil chamber. And define this operator, the sans serif L, which is basically the generator of it's what happens when all of the particles, all the n's, are separated. Okay, so this is the thing away from the boundary. When you don't have any clusters, this is how the system of recursion relations is evolving for the moments. Now you define something called boundary operators. For each I, so these taus are just shifts. It's the operator that acts on a function of the n's and shifts the ith coordinate by 1. And so now you define this boundary operator. And what the result says, the lemma says, is that if you have a function that satisfies that when you apply the boundary operators in the ith coordinate, and then you set ni equals ni plus 1, you get 0. So it's some sort of boundary relation. Then actually the restriction of the action of this sans serif, this free operator on U, is the same as the action of the thing we actually care about. on U. So it's a sort of factorization result. So if we can solve this, if we can diagonalize this operator and find eigenvalues that satisfy these relations, then we actually will have diagonalized L. So this is the idea of coordinate beta ansatz. And it's something you can do. I'll explain how in a moment. Now, where does this come from? Of course, there are many routes to get to this, but one which I'll just highlight, and if you fell asleep, here's a good place to wake up, is the following very nice combinatorial result. So imagine you have an associative algebra in two variables, x and y, that satisfies this particular commutation relation. So it rewrites things, xy and yx and xy. It gives you a relation on that. So now you imagine that you take this monomial in x and y, and you take the kth power of it. When you do that, you expand, you get a lot of things out of order. You have x's before y's, and then more x's, and then more y's. You can use this to normal order. And you can gather things normal ordered, so x's come before y's. And when you do that, you get exactly the same coefficients that came up in the recursion relation for the moments of my beta RWRE. So now if you take a representation of this, where x you think of as the identity and y you think of as the shift map, this is actually proving this result that I gave you before. It's rewriting the free operator in terms of this non-free operator. And the relation, the fact is, of course, that you need to know that these relations hold. So with this in mind, what you're able to do, if you kind of go back to the previous result, we're able to diagonalize this operator. The key here is that you can diagonalize L in terms of kind of products of eigenfunctions, and then you can take sums and different combinations of them, and you can generate a robust enough setting so that all of these relations can be satisfied. The sort of key here is that there's one of these boundary operations, one of these boundary properties for every nearest neighbor transposition in the symmetric group, and that allows you to actually generate a full set of eigenfunctions. And so when you do that, let me come back, and you apply that, and you also need to use a Plancherel theory. A Plancherel theory basically tells you how to do the Fourier transform for this more general operator. You can write down a formula for this moment. You can solve the system. And what it takes the form of is there is a term that accounts for the boundary condition. There is a term that is just from solving the free system, and then there's something that it relates to the initial condition. And there are certain complex contours. So this becomes the generalization of this formula for n choose n over 2 that I teased before. Of course, from here, there's still considerable work. You need to, if you want, for instance, to compute the Laplace transform of the tail probability, you need to now take generating functions in these diverging number of complex integrals. You need to reorganize various terms in terms of residue expansions. And eventually, you get something that you can actually play with and extract asymptotics from. And I won't go into that story, but it is complicated as it needs to be because the limits are themselves complicated. OK. Let me just start zooming out. So for the last few minutes, I want to zoom out. Okay? What I described to you may seem a little ad hoc. You have this RWRE. You happen to look at the moments. You happen to see that you can diagonalize it. You happen to know how to write down these complex contour formulas. That seems very ad hoc. But there is a much more less ad hoc picture that this fits into. So for instance, I mentioned that there is a scaling limit of these random walk and random environment models that goes to the KPZ or stochastic heat equation. And in fact, the moment evolution there converges to a known fact, going back to Khadar and Molchanov, that the moments of the stochastic heat equation solve the imaginary time attractive delta Bose gas. Okay, so this is a well-known result at this point. And in fact, this whole story generalizes considerably and becomes less ad hoc in the context of what are called stochastic vertex models. And while I won't define these, what I will tell you is kind of what are the key generalizations. So this RWRE model actually ends up being related, or in fact a special case of limits of fused transfer matrices that arise in representations of UQ SL2 hat, the quantum group SL2 hat, the R matrix there. The moment evolution equation comes from what's called Markov duality, which is actually equivalent to a symmetry of the R matrix. And the explicit moment formulas actually come from the theory of beta ansatz, coordinate beta ansatz eigenfunctions. So there are ways to write down explicit eigenfunctions that diagonalize these transfer matrices, and one can prove a Plancherel theory. In other words, completeness and orthogonality of these eigenfunctions. Things I should say, here we're always working in the sort of infinite volume setting, and the Plancherel theory is considerably simpler there than when you have boundary conditions. So this story represents one route that people have taken to kind of put this into a grander hierarchy or into a grander scheme, and it's not the only route, I should say. And so what I want to describe now is that over the last two years or so, there's now what seems to be what I would call a complete theory of integrable probability that's coming into focus. So what I described to you is somehow just a one-point result. I said that the large deviation for all the particles started together, large deviations at some later time at some given location has some one-point fluctuation. But of course, you might ask questions like, what if I simultaneously start 15 different species of particles, some of which are concentrated, some of which are distributed in some other initial data, and I look at their large deviations at several different times, at several different velocities. Simultaneously, what is the distribution, the joint distribution of that? So that would be encapsulated in what I call a complete space-time scaling limit. And in fact, we now have a scheme for proving that all of these integral models have the same universal space-time scaling limit. So the scheme, which I'm happy to talk to you about offline, goes by 3 steps. The first is it uses what's called the colored Yang-Baxter equation. This is the Yang-Baxter equation for higher rank quantum groups, UQSLN. And then it goes through an area of research called Gibbsian line ensembles. And the final thing is it uses what's called a strong characterization result for the Airy line ensemble. So from these 3 steps, we've been able to kind of create a general scheme. All of this applies to models somehow in the full space. And we've implemented it for a few. We actually haven't done it yet for this RWRE model. Now, if you think about the RWRE model, you could imagine having in certain space-time locations, particles getting fed into the system as well, or particles being removed from the system, boundary conditions that get imposed on the actual physical system. And it's very interesting to understand the effect of these boundary conditions. And so what we're now developing is the technology, kind of the parallel technology to do this in the presence of a single boundary condition. And then we're developing a technique to glue together these boundary conditions. So ultimately, where the picture goes is that you'd like to understand arbitrary models on kind of space-time geometries that are glued together by increments with different boundary conditions, maybe pants, and then periodic domains, and then things with boundaries on multiple boundaries. And you can develop a sort of stochastic gluing technique, and that's what we're developing, to take together sort of primal results for full and half-space models and put it all together. So in the end, you should get some sort of universal space-time version of this. Okay, the final zoom out I want to do, and this hopefully will kind of get us ready for Norman, is to how should you really think of this in the broadest setting? Okay, so we were interested in these random walk and random environment. This is some classical system. We have some stochastic approximation for it. It ends up relating to quantum integrable systems. What's really going on here is we're trying to answer the question that I think many people are, of how do classical and quantum dynamical systems behave in long time? Okay, that's like the overarching question. And of course, it's important to know, these types of systems come in 2 general flavors. There's integrable models. So these are models where there are many conserved quantities and complicated scaling limits because of these conservation laws. And then there are chaotic models where you have very few conserved quantities, and in the other degrees of freedom, it's otherwise chaotic and effectively modeled by stochastic dynamics. So a real diffusion of particles and all these background, this is chaotic, right? The background is chaotic. It's kind of effectively modeled by stochastic dynamics. On the other hand, things like Toda flow or other KDV, these are examples of integrable systems. Now, what we're finding is that integral probabilistic systems relate to both flavors in surprising ways. So for instance, they arise as Wick rotations of, I mentioned this connection to the imaginary time quantum delta Bose gas, right? So they arise as Wick rotations or gauge transforms of integrable spin chains. There are relations, for instance, between the usual 6 vertex and the thing I call the stochastic 6 vertex. And they also arise as ground states for certain interesting quantum Hamiltonians. And so by understanding the behavior of these integrable systems, you can try to gain some understanding about these integrable quantum systems. Also, there's this connection we saw that exact formulas in the context of integrable probabilistic systems satisfy quantum and also classical integrable dynamical systems. The other perspective is that these integrable probabilistic systems define universality classes that contain the chaotic dynamics. So ultimately, what we're interested in is understanding how advances, such as what I've described in the talk, or this kind of more general theory, in integral probability can lead to some novel and interesting asymptotic behavior about classical and quantum dynamics, and ultimately how this can guide development of future experimental work. Okay, so that's where we're really going with all of this. So I want to conclude. Yes, my brother made the graphics. So there were 2 goals of the talk. One was physical, and the basic message here was that whereas the bulk behavior in a random environment and a non-random environment is the same, the extreme behavior is different, and there's certain characteristics of that, power law and a new coefficient, that captures this and allows you to make some observation about the environment. And we outlined some possible ways to do experiments. And then there was the mathematical goal, which was to highlight the role of integrability and universality. We saw some role of the KPZ equation, or the stochastic heat equation, and this non-commutative binomial theorem. So hopefully I've convinced you at this point 2 things. The first is that I'm not crazy. Okay? And the second, and now just prepare yourself for a bad joke, is that when it comes to the physics of extreme diffusion, there may be more to it than meets the eye in Einstein. Okay, yeah, there was a real, okay, thank you very much.